This is video 1 for chapter 10 on gases. So what we already know about gases is that their molecules are very spread out. So they expand to fill their containers, meaning whatever volume the container is, that's also understood to be the volume of the gas. So if it's in a 1 liter container, the gas has a volume of 1 liter. It also makes it very compressible because there's a lot of space between the molecules, so you can squish them down when you apply pressure so that the molecules can become closer. They also have extremely low densities. That means that there's very little mass in a set volume. So the molecules are spread out, therefore the mass is spread out. So very low densities. We talk a lot about pressure when we're discussing gases. So what pressure technically is a force per unit area. And we will work a lot with what's called atmospheric pressure, which is just the weight of the air around you. So atmospheric pressure is P with a little ATM for atmospheric pressure. And at sea level, the atmospheric pressure is 1 atmosphere. So we'll see that a typical unit of pressure for us is the atmosphere, which is ATM for short. And as you climb a mountain, think about the fact that you have less air above you and therefore atmospheric pressure goes down. So up on a mountain, the atmospheric pressure would be less than that at sea level. So some units that we'll run into. You know, in normal life, we talk a lot about pounds per square inch, so PSI, which is a totally fine unit of pressure. But here we will mostly work with atmospheres, which is little ATM, or what's called torr, which is the same thing as millimeters of mercury. That unit comes from an original barometer where it has a tall tube with mercury. And at sea level, the mercury would rise to 760 millimeters. And that's where millimeters of mercury is coming from. 1 millimeter of mercury is the same thing as 1 torr. Just like 760 millimeters of mercury will be the same thing as 760 torr. Those are interchangeable. And then there's also pascals and kilopascals, which kilo is just, once again, 1,000 normal pascals. So standard pressure is normal atmospheric pressure at sea level. We said that's 1 atmosphere. And to convert it into our other units, 1 atmosphere is equal to 760 torr and 760 millimeters of mercury. And then that's equal to 101.325 kilopascals. So they're your conversion factors. So when we're having to convert between pressure units, that's where you can look. Here's a picture of what I was mentioning a minute ago with a mercury barometer. You've got a pool of mercury with a tube inverted. And as atmospheric pressure increases, the mercury will move up the tube more. So at sea level, it'll be 760 millimeters, which is less than a meter stick. But if it's higher pressure, that mercury will rise, and if it's lower pressure, it will fall. That's where that's coming from. We also can use a system that looks like this, where we're looking for a difference between the atmospheric pressure and the internal pressure of a closed container. And if you have mercury, for example, out here, or a liquid of some type out here moving back and forth, if the level was equal on both sides, that would mean that the atmospheric pressure inside, or I'm sorry, the atmospheric pressure out here would be equal to the pressure inside that closed container. But here, as you can tell, the gas pressure is pushing with a greater pressure than the atmospheric pressure by however much H is. So if we know atmospheric pressure was 760 millimeters and there was an extra 50 here, you would be able to say 760, which is the atmosphere, plus the extra 50 that the gas is exerting. So you can tell that the gas inside is exerting greater pressure. You will run into this thing called STP a ton. So STP stands for standard temperature and pressure. And you want to just have it readily in your mind. So what it is you can always remember the numbers 0 and 1 to kind of simplify it for yourself. 0 degrees Celsius is your temperature, and 1 is your atmospheric or your pressure, which is 1 atmosphere. So here, remember, 0 Celsius is the same thing as 273 Kelvin. So as soon as a problem tells you STP, we automatically know that those are the 2 conditions we're working with. We work a lot with this set of volume. variables right here. We've got pressure for P, volume for V, temperature for T, and moles, which will be a little n. These variables get related to one another in what are called gas laws. So there's several gas laws that help us understand the relationship between these. So really when you're filling up a balloon, just to really simplify it, we are increasing moles of gas in the balloon because we're putting more in there. And therefore we're increasing volume because the balloon's getting bigger. So that's an example of a gas law because it's relating any 2, 3, or 4 of these variables with one another. So the first one we'll discuss is called Boyle's law. And what it looks at is the relationship between pressure and volume. And what the relationship looks like in an equation is P1V1, which means the initial pressure and volume of a gas, equals P2 times V2, which are the final pressure and volume of the gas. So if you increase P here, think about what has to happen to volume in order for the two sides to stay equal. If P goes up, V must be going down. So these two variables are inversely proportional. This is assuming that the other variables are not changing. So temperature must be staying the same and moles of gas must be staying the same. If they're excluded from the equation, we're assuming that they are the same. And if they're not brought up in a problem, we can also make that assumption. So we see that these are inversely proportional. And that should make sense because if you had a gas in a container and you all of a sudden reduced its volume, so you push down on the top, you're reducing its volume, I think we can all understand that that would be increasing the pressure inside that container. Here you can use any units for P and V, you just have to make sure that they match on both sides. Charles's law is going to relate volume and temperature. So here we see that they're actually divided by one another. So volume over temperature equals volume over temperature. So think logically again, if V goes up here, in order for these two sides of the equation to stay equal, if V goes up, then T also has to go up because this fraction or this ratio has to stay constant. So these are directly proportional. When V goes up, T will go up, which also makes sense. If you took a balloon and you heated it up, you increase the temperature, the balloon would increase in size, so your volume also would increase. Of course, this again is assuming that the other variables are not changing, so pressure and moles of gas are staying the same. Here's one really big star here for temperature. Whenever we are using temperature for this entire chapter for gases, you're going to have to convert it to Kelvin. So make sure T is in Kelvin every time you do any type of calculation. Avogadro's law brings up moles. So we actually talked about this one with our gas in a balloon. We see V1 over N1 equals V2 over N2. Once again, this is going to be a direct relationship because if V goes up, N's got to go up as well. It also just makes sense in life because if I increase the moles of gas in a balloon, I'm going to also increase volume, assuming that I'm keeping pressure the same and temperature the same. Those units, the volume can be anything you want, milliliters, liters, centimeters cubed. The N must be moles. So if you have grams, for example, you got to get to moles first before you can use that equation. There's just the equation again as a repeat. We can put any number of these variables together. So all of those laws just simplified it into two variables at a time. This is called the combined gas law, and it can get us to any of those equations. So here we have P1V1 over N1T1 equals P2V2 over N2T2. So what we know is that if we are only looking at P and V, if the N and T are staying constant, you just X out the N and T, and you're back to Boyle's law, which is P1V1 equals P2V2. Or if you're looking at volume and temperature only, then you get rid of the P and the N, you just neglect them because they're staying constant, and you're back to V over T equals V over T for Charles's law. So you can get to any of these relationships through this combined gas law. You just eliminate any variables that are not changing. As far as the units go, remember N must be in moles, T must be in Kelvin, and then P and V are just up to you or whatever's given. We just have to make sure they match on both sides. So here's a few examples of how we would do this mathematically. So gas has a volume of 5.83 liters, and 2.18 atmospheres. So that's my V1 and my P1. So I can already know that I'm looking at volume and pressure. What will its volume be if the pressure is changed to 5.03? So using the combined gas law, I'd get rid of N and T because those are not brought up. And I would get that P1 V1 equals P2 V2. I would plug in my original. So original pressure 2.18, original volume 5.83. And then on the other side, I have changed my pressure to 5.03 atmospheres, and I've left V2 as my variable. So we can solve for V2 by just dividing by 5.03 on this side and dividing by 5.03 on the other side. And here's my final volume. Whatever the units of volume are on the left, that's what we're going to get on the right, because the atmospheres are canceling out and the volumes will match. The next one, really you can let the units help you a lot. I see liters, which means I've got volume involved. I've got Celsius, which means there's temperature. Constant pressure, meaning I'm not going to have to deal with pressure because I only care right now about things that are changing. And it says, what will the volume be at the higher temperature? So I'm working with V and T. So I go to the gas laws and I find my relationship. And then I remember that temperature has to be in Kelvin. As a reminder, you'll add 273, so 15 turns into 288 should be here, because 273 plus 15, this should be 288 right here. So we've converted it to Kelvin. I just made a mistake right there. And then 40 degrees Celsius plus 273 does give us 313. So we change them both to Kelvin. And then we take our original volume, which is 1.20 liters, and then we find V2. I recommend cross multiplying, which is what I've shown up here. You can do this algebraically however you want, but be sure that we're getting the same answer. So I would take 1.20 liters times 313 Kelvin and put that on one side, like I've done, and then cross multiply the other way. So 285 times V2 on the other side, and then it becomes easier to find volume. So we divide by 285 and divide by 285, and my new volume is 1.32 liters. Okay, and then the next one says if at STP, so remember that automatically means that I'm at 0 Celsius and 1 atmosphere. So the volume of the gas is 6.29 liters. What would it be at 1.86 atmospheres and negative 35 Celsius? And it reminds you here what STP is. So what we notice is that we have volume that's changing, we have pressure that's changing, and temperature. So we have 3 variables this time that we've got to include in our equation. So moles is the only thing we're leaving out, the little n. So here's our gas law. And we plug in our atmospheres to begin with, which was 1, 273 Kelvin, because that's STP, 6.29, that was the original volume. And then on the right side, we have changed the pressure to 1.86. We have changed the temperature to negative 35 Celsius, so we add 273 and get 238. And then we're looking for V2. Again, I'm going to ask or recommend that you cross multiply. So 1 times 6.29 times 238 goes on one side, and on the other side goes 273 times 1.86 times V2. So we get everything just in this linear equation here, and then we just divide. So to get V2 alone, we're going to divide by 273 and divide by 1.86, and here is our new volume.